the power grid model that I'm going to show on this next slide right there on the right. This is the IEEE 14 bus case. And uh, um, do you know the history of this case? And there's some other ones like it that are the IEEE standard transmission test cases. Um, a lot of these were designed and created in something like 1960s, 1970s, and particularly for the um, where they originally came from is some kind of approximation or aggregation of real U.S. Electric grid models. And um, uh, these have served our community very well over many decades. And if you read the literature in power systems area, IEEE journals, things like that, you're going to see a lot of papers written which prove various algorithms and methods and do demonstration test cases on IEEE 14 bus case or 118 bus case and some other ones like that. However, over those decades since these grids were created, the real electric grid has changed very dramatically. And I can show on the next slide, this is what the real US grid looks like now. This is from the US Energy Information Administration. You can just look up the Energy Atlas web page. And um, so it's pretty obvious in some ways the difference between the two. And this is really the beginning of the motivation for this research is saying, well, um, in the power and energy area, we want to be designing new research ideas, new methods, new algorithms, which are able to be run on real electric transmission networks. In practice, if you take the Eastern Interconnect in North America, today's actual transmission grid models are somewhere in the neighborhood of 80, 90,000 buses, something like that. Going back to the previous slide, in addition to real grids just simply being larger in terms of the number of buses compared to these test cases, it's not just the size, but it's also features and complexities, things like tap changing transformers, impedance correction tables, remote generator regulation, just to name a few. Another one, of course, is just the different approaches to voltage control with several synchronous condensers being in the older models, as well as renewable energy generation, which was relatively small when these grids were created. So this is a gap that was kind of identified several years back, and the goal of this research is can we build some new generation of test cases that reflect the electric grid today? And one of the things you might be asking in this is, well, why can't we just have a model of the real electric grid and use that for our research? And I certainly want to be the first to acknowledge that um, that we do want to be using the real electric grid as much as we can. And there's really no substitute for testing new ideas, new algorithms, new advancements on anything other than the real grid. There's no substitute. However, one of the big challenges in using real grid models is this designation of critical energy infrastructure information. And this goes back to essentially the 9/11/2001 terrorist attacks with a growing concern for security of critical infrastructure. So there's legitimate national security considerations at play. And as a result, actual electric grid data, much of it is not able to be publicly shared, is under confidentiality requirements. And even though some researchers can get access to actual electric grid data, it's provided under non-disclosure agreements, and it's not something that you could publish in a paper with full detail. So there's still a need for test cases, but there's a gap here. And the goal of building synthetic power grids, which is what we're talking about today, is to drive innovation on the grid by providing test cases that are larger, that are more complex, and hopefully that are matching the real grid in terms of being realistic a little bit more, while still maintaining the public nature of a test case like the IEEE test cases, so that they can promote open science and in power engineering. Tons of applications for this research, and I'm excited to share just a few of them today. Okay, so I'm just going to start right at the very end, which is the following. So if you look at this grid right here, this is our synthetic 70,000 bus US Eastern Interconnect grid. And if you look at this and you compare to the previous slide or to some other knowledge of the actual electric grid, you might think, wow, we're able to release on our website there the actual US Eastern Interconnect electric grid. And however, if you are more familiar with the real US grid and you look more carefully at this grid and you zoom in, you will be totally at ease, because you will find that this grid does not in any way specifically model the real transmission lines, substations, and loads of the real US grid. It's a fictitious case. So it's created by an algorithm. It's created by a synthetic process. So therefore, this is a public test case, and is really readily accessible for research and development. It does match in size, as you can see, actual grids. We also have done a lot of work to ensure that this grid, from various points of view, is realistic and matches some actual validation metrics against actual data systems. So we're going to dive into some of the more detailed aspects of both creating and validating and then applying the methods for creating synthetic grids today. Okay, so how do we build synthetic grids? This one on the right is another one. This is our 2,000 bus synthetic Texas grid. I think this is probably the most well-known of our synthetic grids, also available on our website. The first thing you might notice, if you are familiar at all with Texas, and keeping in mind that this grid was built in 2015, and Texas grid has changed significantly since 2015. You'll notice that you see that the generation is located in roughly the same places that it is in the real grid. You can see that there's 2 nuclear plants, as Texas has. The gas and coal plants are in approximately the right locations, although some of those coal plants have been retired since this grid was made. And you can see the wind and solar in the western part of the state. If we were to do one, and we have done one for today's Texas grid, you would see a lot more of that green and yellow in the west and other places across the state. But the point of all that is to say that generation data is not critical energy infrastructure information. So generator data is public information. You can go to the EIA website and download the list of generators, their location, their fuel type, their capacity. So we start with realistic generation. Load data is not quite as easily available, but we make some assumptions that load is going to be related to population, or you're going to have more load where there's more population. We do some other techniques to get an approximation for the load. And so as we're making an electric grid for the synthetic test case, we're roughly following the same procedure and general strategy that is used in actual electric grid transmission planning processes. So the first step in this is what we call substation planning. And for substation planning, as I mentioned, we're going to start with public data to get us the seed for the generation and load. And then we have some clustering techniques that are used to create synthetic substations, buses, and transformers. And then the most complex part of this process is the transmission planning process, where we have an algorithm that I'm going to go through in this in this presentation to place the transmission lines and transformers so that we can connect the generation up with the load that in a way that matches various metrics, both topological and geographic, as well as electric and engineering requirements for the network, and do this in a linearized DC sense, followed by a detailed AC power flow through a reactive power planning algorithm. Helps us get a convergent Newton-Raphson power flow and the appropriate voltage control devices. Once we have a power flow, that's the jumping off point for various extensions on the grid, which we'll go into as well. One thing to notice about this grid is that we have 500 kV, 230 kV on the Texas grid. And if you know about the Texas grid, the fundamental voltages in most of the Texas grid are 138 kV and 345 kV, although there are active plans to extend with a 765 kV network as well. But for the purposes of this particular grid, we just chose different voltages. It's not that there's anything fundamental about why those voltages were chosen for Texas. It could just as easily have been these other ones. And the benefit is it serves to highlight the fact that this is a totally fictitious network and does not in any way reflect the real transmission topology of the state. Okay, so zooming in on these steps a little bit more detailed. Substation planning, I mentioned it's seeded by the public energy and census data, energy data for the generation, census data for the load. Yeah, for large systems, we do have to think about this and decouple by area, because you'll find that in a real grid, various areas are more interconnected with each other, but not as tightly interconnected with one another. So we take that into consideration. And we use a modified hierarchical clustering technique that takes the zip code fragments and the generators and then clusters them into a reasonable set of electric substations. We also need to assign which substations use which voltage levels. And so we use another clustering algorithm for that. And we need to take into account when there are multiple areas that have different voltage levels. We need to make sure that we have cross-area connections. Once we've got the substation planning, we need to figure out what is going to be the dispatch of the generators and the loads in order to do our transmission planning. And so that's why we do an economic generation dispatch. We assume peak planning load. Generally, this is a common practice for doing the first order transmission planning. Would be to focus on the peak load and economic generation dispatch. So that's kind of our starting point here. In the next step, we use synthetic transmission planning. And one of the key things that we mentioned when we're doing transmission planning that's really fundamental to our approach is recognizing that geography drives transmission planning. And you saw that on the map I showed at the beginning of the presentation. Geography drives transmission planning. You can't just build a transmission line anywhere. You're constrained by the geographic features. And so that's one thing. Another thing to consider is the network topology parameters. And so this is recognizing that there are consistent and recognizable graph metrics that appear in real grids. And one of the things that goes along with the topology is recognizing that anytime you model the electric grid as a graph, you need to think about your modeling of the graph to make sure you're being precise. For example, if you use a bus branch topology versus a node breaker topology versus a substation line topology, those are going to give you different graph properties. And I don't think I included my slide on that for the sake of time. Yeah, but we've done some analysis to show that you really need to have some consistency if you're going to use graph theoretic properties in constructing realistic grids. In addition to those structural characteristics, we also have some power flow feasibility characteristics. We want to have a good power flow result, both in the base case and in the n-1 contingency conditions, and a good result defined primarily by avoiding transmission line and transformer limit violations in those conditions. And so this is a difficult problem for large grids. One of the aspects is that there's a very large number of possible branches, right? If you have, it's going to be on the order of n squared if you have n substations. There are also many competing metrics to meet. Obviously, power flow feasibility is in competition with geographic constraints, for example, and you have to get that balance just right. We also have to consider the fact that there's overlapping voltage networks. You can't just connect a 345 line up to a 138 kV bus. If you are considering the contingency conditions, that increases the computation even more. And we're always going to have some manual adjustments, but we want to try to keep those as low as possible. Okay, so what does our solution look like? I show there on the bottom kind of just a conceptual idea of how we start. First of all, I mentioned those n squared possible lines. We use the Delaunay triangulation, which is a computational geometry technique, as a nearest neighbor proxy. And if you consider the Delaunay triangulation plus third neighbors on the Delaunay triangulation, that means any line which connects two substations that have a distance of 3 or less along the Delaunay triangulation, you cut the number of transmission lines from n squared down to 21n. So if we take Texas, right, Houston and Dallas are so far apart that you're not going to have a transmission line directly connecting the two of them. And so you can eliminate a large number of lines that are so long or so infeasible that you would never build them. And the Delaunay triangulation helps us to do that. We did some studies on some real grids, and we found that 99% of lines, it's actually 99% plus, and that also excludes some that are in there from bad data, can be found on this reduced search space. We begin with a randomized graph. You can see that on the second plot from the left at the bottom there. Obviously, that's not a very realistic electric grid. We have an iterative process that starts from that initial condition and moves step by step into a higher quality network. As you can see from the second from the right there, plot would be after several rounds of iterations, and then the plot at the bottom right would be at the end of the methodology. This iterative process considers the n-1 contingency analysis as well as the graph theoretic and geographic constraints. And in order to consider the n-1 contingency analysis, we do use DC power flow, but we have this sensitivity metric that we applied. It's kind of similar to a line image sensitivities, and we formulated in such a way that we can very rapidly calculate for over 100,000 candidate lines in this case. And there's some papers that show the details of how that sensitivity metric works. You have to kind of parameterize this model to get the right balance between the fixed costs and the network and simulation performance, so that we end up with a realistic grid. But overall, the algorithm is pretty successful at achieving that with the right parameters. And then at the end, we want to make sure we validate the metrics that we want to meet against the ones collected from actual grids. Okay, the third step is the reactive power planning. If you've ever used Power World Simulator, you've probably seen a box like this one on the right. You have a nice, perfect DC power flow solution. Everything looks good. And you click solve for the AC power flow solution, and you get a Newton-Raphson divergence. And it says we can't solve it, and Power World will tell you a blackout. Often the flat start doesn't converge, even if there is a good solution, but most of the time there isn't a solution. If you have a real grid, they don't run into this problem very often, or at least it's easy to get around this problem a lot of times, because you have the ability to start with a prior solution and then try to make a small change and hope that you get a good solution from that. Doesn't always work for new synthetic grids. We're starting from scratch. We don't have a solution. And we don't even know that there is a solution without sufficient reactive compensation. So what do we do with this problem? We have developed a method that involves an iterative transition from the DC solution to a realistic AC solution. So step one for this method is to add a temporary generator to the highest voltage bus of every substation. This would be a generator with 0 megawatts, but it would have unlimited reactive power, or at least a very large capacity for reactive power, both positive and negative, controlling that bus voltage. Obviously, this isn't realistic because we're not going to have reactive compensation at every bus, but it gets us a starting point where we can get a AC power flow solution. With this AC power flow solution, with a large number of PV buses, we can begin to iteratively move towards something a little more realistic. We take advantage of the fact that reactive power is generally a very localized phenomenon, and therefore we can do multiple zones of the grid in parallel, and we end up removing most of those temporary generators and adjust the properties of the others until we have a relatively small set of reactive power resources that we need in order to put our shunt capacitors and reactors in place so that we can get a good AC power flow solution with a good voltage control performance. So that's a summary of our synthetic reactive power planning procedure. And so here's some results. This is a 10,000 bus case for the Western Interconnect of the US. Initial power flow solution diverges, and we end up only needing about 8% of the substations to have shunt capacitors on them. And this is actually a lower percentage than you typically see in the real grid, which is good. Gives us the opportunity to have some room for some additional ones as needed. And if you look at the voltage profile there, you can see the comparison of the synthetic grid in yellow distribution against the other grids. Okay, so the results of this long process are that we have large stalled power flow cases that don't contain CEII, which is good. They're also highly realistic because we're meeting a bunch of different characteristics. But we also want to be able to show that they're highly realistic. And this is a really complex problem for a number of reasons. But to attempt to attack this problem, we have collected validation metrics from many actual US electric grid cases, which help us provide a check on the case quality. There's a lot of variety in engineering design and practice. Actual grids are quite diverse. Some of the metrics are kind of listed here. I've kind of touched on several of them already. We have a couple of papers that go through a lot of them in detail. And the point is that we do validate across a large number of metrics to make sure we have good device parameters, we have a good technical performance, and we have a lot of things related to the topology as well, checking things like the cycle basis, surge impedance loading, clustering, radius of the grid, and average shortest path length. I think there's always room for improvement. I think that there's new metrics that we're looking at and trying to make sure the grids match. But I would also add that there's a lot of diversity in real grids, and just because one particular grid has a certain characteristic doesn't necessarily mean it's a requirement for all real electric grids. And in fact, we found some properties that did vary fairly widely from location to location, which can be partly due to geographic constraints or geographic requirements, and can also just be a matter of engineering design choices and design philosophies. So briefly, I want to summarize some of the impact of synthetic grids. The biggest one I've already mentioned is it just creates higher quality, larger, more complex, and more realistic test cases than existing ones. It allows for an improved ability to cross-validate published research results in power system literature. So I can write a paper now, I can try it on this 2,000 bus Texas grid, and I can give you not only my results in my paper with all the data and everything, but I can give you the full transmission grid model and put it out on the website so that you can download it, check my results, and run the algorithm for yourself on the same data. This is, I think, tremendous ability to improve academic research, and as well as having hopefully an impact on industry as well. And for industry, I think one particular benefit could be the ability to demonstrate new capabilities without having to compromise sensitive data. So you know, if you have someone that you're working with that wants to demonstrate or test some new capabilities, or if you yourself are internally demonstrating some new capabilities and want to give data out, information, and kind of show off something cool, synthetic grids could be a platform for doing that without having to worry about confidentiality. Geographic embedding, I think, is a tremendous part of this. It allows us to do some other geographically related things. One project we worked on a lot in here at A&M is on geomagnetic disturbance and the possibility for a rare solar event to cause a voltage collapse on the electric grid. And so this is just a picture here showing a potential application of that. We've also done some more recent work on higher quality dynamic models for transient stability and EMT analysis. And I'm going to show a little bit of that on the very next slide. So yeah, so synthetic grid dynamics is a whole different area. The basic idea with this is we want to augment the power flow case we already have with dynamic models. There are a large number of models with many parameters that need to be tuned. It's not sufficient just to match the statistical characteristics of the parameters themselves. But we also need to be able to match the overall system frequency response characteristics and other performance and dynamic requirements. So this is a big project. We've got this paper that is mentioned right here. We also have another one that just recently got published that I can share as well. And we can create this. We have this out there for the Texas 2000 bus case, and we've even got some updated ones with more wind and solar models. But I've got a video here I can show that basically what this is going to show is a frequency response plot for this synthetic grid, where we're going to be opening up a generator in the Gulf Coast region and watching the frequency response. Your response happens, and you can see the oscillations from one side of the network to the other. And then you can watch the grid stabilize to a certain frequency that's a little bit lower than the nominal value due to the droop control. So that is the synthetic dynamics. And of course, you can do this with a real grid as well, but it's just an example also of how various dynamics-related research could be demonstrated and used using these synthetic models. And we've done some analysis to check that things like frequency nadir and settling time are commensurate with various realistic grids. A few other things I want to kind of show from some research work. We have done some combined transmission and distribution synthetic grids. So this is a major undertaking here that we worked on in collaboration with some partners at NREL as well as Comillas University in Spain. And they did most of the distribution work and we did the transmission work. So this is 7,000 transmission buses for a Texas grid, but then there's something like 10 million distribution nodes in this grid. And you can see that it goes all the way down to the meter, zooming in. And, you know, this is a much larger test case and data set than I think is even used practically in industry for almost any study. But we recognize the fact that the interaction between transmission and distribution is definitely an ongoing area of research, particularly as more smart devices are connected to the distribution side, rooftop solar, electric vehicles, customer connected generation and batteries, things like that. And so we hope that this data set could be part of advancing research and development in that area. I mean, this case is so large that it's really hard to even get a solution. It's really hard to even make this picture, to be honest. And so the benefit of this data set would be even computational research towards, you know, how can we even solve a system this large and get some benefit out of it. But at least now we have the data available and we have some opportunity to do some research on this moving forward. Another one is combined electric and gas grids, going back to the idea that geography drives transmission planning. And so having geographic embedding of the transmission network allows us to do geographic connections to other networks. And in this case, we have these synthetic natural gas networks that were built by a grad student working with me. And so we can look at things like combined electric and gas interactions. In particular, we were kind of looking at the aftermath of the 2021 Winter Storm Uri events, in which there were some adverse interactions between the electric grid and natural gas network that could potentially be aided by better coordination between the two. And so this is a data set to begin to explore research in that area. As an educational institution, I really see a huge benefit of synthetic grids being in the educational space. I love teaching our senior level power system analysis elective class. And this class has a lab that involves transmission simulation exercises. And these synthetic grids have transformed that class because we're able to use realistic large-scale grids without having to I mean, we couldn't do it for real grids because of the confidentiality restrictions, but we can with synthetic grids. And so the students in the class get experience using large realistic grids. And this has really two main benefits. One is I think it's motivating because the students recognize Texas, they recognize a realistic case, and they can kind of connect this to the real world problems. And second, I think this kind of exercise gives students more of an appreciation for the sort of challenges and difficulties that are involved in real transmission grid analysis and planning. So like this exercise on the left is where we're looking at how are prices affected by various transmission outages, and kind of how does a network wide locational marginal price analysis work. And then the one on the right is a dynamics analysis. And then we've even got it set up in a real-time environment where students get to sit in the operator's seat and try to prevent a blackout in this hypothetical scenario on the Texas grid. So education and training. We also have short courses for industry as well that involve these as well. Just want to mention the ARPA-E Go competition, which is wrapped up last year. We used our cases were used in this competition. This was something that ARPA-E through the Department of Energy was working on helping to spur innovation in the area of grid optimization. And this is just one example of the kind of competitions or analysis and open science activities that can benefit from having these realistic data sets. We do happen to have much of the data for these available on our website. And our work here kind of involved creating some difficult realistic problem scenarios to enable evaluation of competitors in a meaningful and useful way. Okay, so that's kind of the end of the synthetic grids. I want to share some other study results here for a very related problem that we're just getting started on to kind of show how these results can also be applied for things that are not just synthetic or fictitious, but for something realistic. I'm just going to kind of zoom through these. But first of all, the motivation for this is really the following chart. And it's not unique to Texas, but Texas, I think, is really significantly feeling this, which is that the load is growing, not at a rate previously seen. And a lot of this is associated with data centers. So you can see here, growth through 2025, modest, stable, predicted growth over the next 10 years, something like doubling the peak load as well as the energy consumption. And more than doubling the energy consumption. So what is the takeaway from this from a transmission point of view? Well, the takeaway is, of course, part of the issue is there's going to be a need for more generation to match this load, but then there's also going to be need for more transmission on this load, on the grid to meet this load. So this brings us to the transmission expansion planning problem, which is a problem that has been around for many decades, but has really many very notorious challenges and to solve. But basically, the transmission expansion planning problem is, okay, we have today's grid, and we know what load and generation is coming online in the future, and we want to figure out what transmission lines we want to build, and what lines we can do to minimize the investment costs, and to have sufficient network reliability and efficiency. This problem is really difficult. Because the possibilities are so large. You've got something like n squared possible lines that could be built. The search space is really large. And so it could be viewed as an integer programming problem, but you do have cursive dimensionality with this problem. One of the other challenges that makes this problem hard is that even if you have a candidate future grid that you would like to evaluate, you really need a very complex and detailed modeling and analysis process in order to check if that's a good candidate, one potential solution. Things like power flow, contingency analysis, not to mention dynamics and stability, voltage control, things like that. So what do we do? Industry practice, to my knowledge, there's very little application of integer programming methods, and typically the method is to pick relatively small number of possible solutions, kind of hand design using engineering judgment, figuring out what transmission lines might possibly be good to build. And then for each one of those, try to run a detailed economic and engineering analysis to pick one. And of course, that has worked really well for us. But I think that there could be a possibility of missing better options we hadn't thought of merely because each of those individualized studies does take a tremendous amount of work. Okay, so why am I bringing this up in the discussion about synthetic grids? Well, we recognize that there is significant overlap between the problems that have been solved for the purpose of building synthetic grids and the problems that exist for potentially running transmission expansion planning. And so this figure shows a very similar grid to the one I showed before, but you can see the generation has changed. We're assuming a lot of new generation that's coming online in Texas, and we're assuming a new growth of load. And basically, the idea of this preliminary study was to look at the potential for using the synthetic grid building algorithm, what I was talking about, the iterative removal and iterative addition, to try to solve the transmission expansion planning option. We used a very similar process as before, where we began with the prior transmission network and we kept those lines and we used our iterative addition and removal in the same style as the network synthesis. The candidates come from the Delaunay analysis, same as before, and we also still apply the N-1 contingency sensitivities as well. We used just a desktop workstation, used 24-hour computation time, and I just want to kind of highlight that this process is basically taking the opposite or inverse approach of a conventional integer programming approach to transmission expansion planning, in the sense that we are focused on starting with something very scalable that can get some kind of solution without necessarily having the optimality guarantees that an integer programming approach would have, with the goal of eventually improving this process toward the ability to have some more rigorous optimality guarantees. Still getting there, but this is kind of the results of this study. Shows the new transmission lines that were added by this example. And kind of as expected, these new transmission organized around where a lot of the new generation was in the western part of the system, and in a general backbone overall, including along the Gulf Coast where new solar was added. This picture I should explain. It shows the new lines added in red there from these study results. So that's just a preliminary study. I've got a paper with a lot more details on kind of what we did here. That is my main contribution I wanted to share with you all today. I want to emphasize again what I said from the very beginning. There's really no substitute for running studies on the actual electric grid. The purpose of synthetic grids is really to pave the way for doing things that can work well on the actual electric grid, and to kind of bridge that gap between the IEEE test cases and the real grid. The goal is to spur innovation for modern, public, high-quality, scalable test cases for power systems, research and development, and education. And I guess with the title having the word open science in there, I really want to move toward higher quality research in our area, and that means research that is able to be cross-validated and tested and reproduced. And synthetic data, public data, open data has a lot of potential to contribute to that. And the final message really here is that our synthetic grids are available for your research. And we're always looking for feedback to improve them. So I encourage you to take a look at our website, see if some of these data sets could be useful for you. And yeah, let me know how you're able to use them for great things. So I appreciate everybody's time and listening today. That's the end of my main presentation. I'm going to be able to have some time to take some questions. So Koji, are we ready to move forward with the questions?
Yeah, thank you for the very impressive presentation today. We have already had some questions on chat window, but before
Okay,
that, I just have just quick question.
sure.
So yeah, you mentioned about the transient stability in your
Yeah.
slides. And then transient stability is generally treated as an angular stability, not a frequency stability. And in your display studies, they are mainly for frequency stability results. And then can we use the same system model data for angular stability, specifically like a power swing oscillation following the disturbances?
Yes, definitely. So frequency stability and angle stability are two different phenomena that are important for stability analysis. But time domain transmission stability modeling is a fairly general stability analysis technique, which has the capability to analyze various phenomena, including frequency stability, as well as angle stability, and as well as, to some extent, dynamic voltage stability by just having models that are appropriate for the time scale of milliseconds to seconds. So definitely that is something that this model is capable of studying.
Okay, thank you. And then also, do you have like a off-the-shelf data set for a particular software like a PSSC or Dixieland or maybe
Um,
Per World?
yeah, good question. So most of these data sets were developed originally in PowerWorld format, but we released them on our website in a variety of different formats, exported from PowerWorld in most cases. Um, I I know that for some of them, they require a little bit of extra work to get them to run properly on other systems. And I know I wish I, of course, had the time and ability to validate them all on all the other formats, but at least it has a starting point in a variety of different formats, including like the PSSC RAW format, DYR format, um, and Map Power, for example.
Yeah, so probably it is easy to convert from one to another for power flow data, but in case of dynamic models, I think, as far as I know, I have never heard a very efficient converter from one software to another. So
Yes,
even if we have the dynamic data for power world, but can we convert the dynamic model data from power world data to, for example, PSSC dynamic data? It is
we
possible.
can we can convert the data, but there is still a significant challenge to kind of clean up the result and make sure that it runs and gives you the same results that you expect in PSSC. And we haven't been able to do that very much, mostly because we don't have a PSSC license or the bandwidth to do that. But um, the initial data, the DYR file is there, and they're standard models.
Mm.
And I know that yeah, there's been a lot of effort to look at those compatibility issues. I mentioned EMT. We've done some initial work on EMT for the synthetic grids. That's a far more difficult data challenge in terms of interoperability.
Thank you. So, Adam, can you open the chat window?
Yeah.
And we have like a 3 questions at this
Okay.
moment.
Yes. Let's see. Okay, so the first question is associated with the reactive power planning part of this presentation. So with the reactive power planning, the question is, what sensitivity parameters go into the calculation of shunt capacitors for reactive power compensation in these synthetic grids? Um, okay, so if I understand the question correctly, we're talking about mainly this slide right here, I guess. And we are the approach that we're using is to run these as PV buses in the interim. And so as PV buses, they're going to be in the Newton-Raphson power flow, they're going to have unlimited reactive power, or at least a large range of reactive power capability, and they're going to be regulating the voltage magnitude. And then when we finalize the case, we take those reactive power resources and we turn them into capacitors or reactors. So there really aren't sensitivity parameters in terms of the calculation of these, but it's really the result of the iterative process that leads to voltage control solution. Let me see if I have the word sensitivity on this slide. It might be needing to comment on something that I said here. I don't see that. So if you want to provide more detail, feel free, but that is my best interpretation of that question. So thanks for that question. And the other one by the same person is, do you need the wind PV penetration in order to calculate the exact shunt capacitors you need for reactive power compensation? So this reactive power planning approach is based on specific load conditions and specific generator dispatch conditions. And as part of that generator dispatch conditions, we do make assumptions about how much wind and solar is in the case. And so, yes, we do consider that. So I think the answer to that is yes. Question is the real-time synthetic grid implemented on a real-time simulator like Opal RT or RTDS? It has not been by me, but the data set is publicly released in a variety of formats. And I would not be surprised if someone has done some work in a real-time simulator with them. They're very large, and so I think you would need a very large real-time simulator in order to use them. But if anybody knows about that, I'd be interested to learn. I have not done that myself, but it's certainly something that could be done. And then there was a question about small modular reactor nuclear power generation trend and its implications, if any, on the next generation grid optimization. Okay, so this is a good question. This is definitely an area of potential research moving forward. It's hard to know what will be the future of small modular reactors. But I will say in general, kind of going back to this slide here, that I think transmission expansion planning is going to be very important because the load growth is going to require a lot of new transmission. And it's also going to require a lot of new generation. And to what extent that new generation is conventional nuclear, small modular reactors, wind, solar, natural gas, to what extent batteries play a role in that, is definitely going to affect things. But I think regardless of those things, you're still going to need transmission. And we need to be strategic about where the new transmission will be. So that's definitely, I mean, could be a consideration when it comes to running these transmission expansion planning studies. So thanks for that question. I see one more that just got put, well, I see, okay, there we go. Got a couple more there. Okay, there's a question about the validation metrics and to what extent they turn out to be useful and consistent across different regions, and to what extent they maybe would be more specific to a single region. I guess I can give a few examples. So one very surprising example was degree distribution. So degree distribution is the average number of transmission lines connected to any particular node. And there's actually a wide disagreement in literature about degree distribution. And I think the main reason for that is that there's a lot of the literature is not properly considering how you model the power grid as a graph. So do you consider transformers to be a branch, or to consider them to be part of a substation node? Do you consider voltage levels independently or together? Are you using bus breaker models? And so forth. And that has a huge impact on degree distribution. Or I should say average node degree and degree distribution. But what we found when we studied degree distribution in real grids using a consistent modeling framework, we found extremely consistent average node degree, and it was around 2.6. And we also found a relatively good agreement in terms of degree distribution as a whole. So that was one example of something that was pretty consistent. We've got a lot of different ones. In terms of what was something that was very different from grid to grid, I mean, there's a number of examples. I mean, a lot of them are driven by geography, right? So if you do something like average length of a line, that's not going to be the same in Texas as it is in New England or Hawaii, obviously, because the lines are bigger in Texas. And so that just the length, geographic length affects a lot of things, right? The line impedance distributions, the electrical distance across a network, things like that. I would say a lot of things are also affected by the specific voltage levels considered. So if you have a 500 or 765 kV network, your reactive power metrics are going to be very different from if your highest voltage is 345 kV, because with those higher voltage networks, you're going to have a lot more shunt capacitance and therefore a lot of reactive power supplied by your transmission lines. So that'd be a couple examples. There's a bunch more, but that's a couple of examples of how that goes. Okay, one question is about HVDC. We didn't really do a lot of HVDC on these synthetic grids. In reality, HVDC has a small number of transmission lines in the real grid, and even though it does have an impact and is interesting, that really didn't affect our algorithm, because generally we kind of add those on a case-by-case basis. So really don't have too much on there. Okay, I've also got someone with a hand raised. Do we want to take that, or do you want to put your question in the chat?
Can I go ahead?
Yeah, go ahead.
All right, thank you very much. I would want to find out what, with regards to have you considered the reactive power reserve margins in the synthetic environment, especially when you're modeling grids that have a very high variability in renewable energy generation?
Yes, that's a good question. Yes, that was one metric that we looked at, was how close are the generators to their reactive power limits, and so how much extra reactive power we have available in the system. And that's also reflected in N-1 contingency analysis, where we look at whether there's enough reactive power not only for the base case but also for the contingency conditions. There's a variety of ways to quantify the reactive power sufficiency, but we did look at a couple of things in that area. So.
Okay, my name is Anthony. Can I reach out to you after this to follow up on some of my other questions? Because of the time, I don't want to go further.
Sure. Thanks for the question.
Yeah, so Anthony, so the Adam's email account is available on the internet. Just you can type. Oh yeah, also yes. So please use his email account to reach out to him.
Okay. All right. Thank you very much. So Professor Adam, I will reach out to you. My name is Anthony, by the way. Thank you.
Thanks.
Sounds good. So I think the time is almost over. So let's close our webinar today. So next time we're going to invite a professor from Brazil, who is currently a vice chair of the RGB Power System Dynamic Performance Technical Committee, to showcase the Brazilian blackout event caused by inverter-based resources. And then the webinar will be held sometime in November. So please periodically check the Archway Footage section website. And now I also upload the flyer to the Archway V tools shortly. So anyway, thank you for joining us. And then also Professor Adam Birchfield, thank you for very impressive presentation today.
Great. Thank you very much.
Yeah,
Thanks,
thank you for
everyone.
everyone. Yeah. Enjoy the rest of the day. Bye for now.
You. Koji,
Yes, I'm here.
did you forgot to give him a $25 gift card?
Yes, yeah, I will send him the $25 gift card
Okay.
later on.
Okay.
Yeah.
Great. Very good, Koji. Thank you very much. Yes. Very
Yeah.
good.
Thank you, Max, for
Okay.
joining
Okay.
us.
Thank you.
Yeah, bye for now.